this topic is really useful because what you get, and I don't have sometimes I have an actual little physical device, but I don't have that, is that if we set this up so you have a loop that can rotate in a magnetic field, then what it gives is that it sits there and you bump it and it starts and it just turns and turns and turns. And so what you're making here is a motor, an electric motor. So by running the current through the loop or through the armature of the motor, then it's going to cause it to rotate. And so round and round and round it goes. And we essentially made a very simple electric motor, which, as you can tell, is a fairly important concept to us out of this particular topic. Okay. So, but that means that leaves us with the last little bit. And the last bit is the fact that we can create magnetic fields with current carrying wires. Okay, so let's go in and let's just be in general. So magnetic fields created by, and number one, they're created by, net magnetic moments of the particles that make up the atoms that make up the matter. So this is your standard, we have a magnet. We have some sort of, ferrous material. So they have net magnetic moments. So instead of having like with charge, where you have equal numbers of electrons and protons, and then the net charge is zero, what you end up with is that you can end up with configurations of electrons orbiting your atom in which you end up with a net magnetic moment. And this is because of the fact that the electrons themselves behave like a little magnetic dipole, like a little compass needle. And so they have a magnetic moment, okay? And so it can just be part of the matter. And then the second option for creating magnetic fields is we can create them from currents. And so if you have a moving charged particle creates currents, then they will also generate magnetic fields. And these currents create the magnetic fields, essentially due to Ampiere's law. But we're not directly going to talk about Ampiere's law. And that's probably pretty good. Ampiere's law is challenging to do. So I think it's okay that we're going to opt out of directly addressing Ampiere's law in this class at this level of mathematics. So I think that's okay. And so what we're going to do, though, is we're going to give you the results of using Ampiere's law to current carrying wires in 3 different configurations so that we have a formula to use to calculate magnetic fields. Okay. And that's where we're going to go. So we're going to consider We'll look at 3 different configurations of, current carrying wires to create magnetic fields. And so those are going to be, we're going to look at what they call the long straight wire. Current carrying wire, of course. We're going to look at a flat circular loop of wire that carries a current. And we're going to look at a solenoid. And so a solenoid is essentially like a cylindrical coil of wires. So we take a bunch of wires and wrap it to make a little coil, then that's a solenoid. So okay, so it's like a little tube of wrapped wires. Okay. And what's important about the solenoid is that this is the magnetic equivalent of our parallel plate. And you're like, well, what does that mean? Well, the parallel plate was the configuration where we had a uniform or constant electric field. And so the solenoid is going to be the configuration where we have a uniform or a constant magnetic field. The parallel plate was kind of the generalization for creating a capacitor, which then became a circuit element that allowed us to store energy in terms of the electric field. The solenoid is going to be the ideal case for creating an inductor, which will then store energy in the form of magnetic fields. And so it really is the analogous quantity to like our parallel plate. So we're going to talk about how to find our magnetic fields from these current configurations, and we'll write down the formulas. These aren't ones we're going to derive or anything like that, because otherwise we got to go back to Ampiere's law. And so we're just going to state our results. And then we can go in and do an example or so of using these to find other stuff. Okay. And so this will be very similar to we can now calculate electric fields. And so then we can do all sorts of fun, vector problems, where along the line is it going to be 0? What's the net magnetic field at this point? And, so on and so forth. Okay.